SwayamPrabha. Digital India. Educated India.
Hello, in this video we are looking at the analysis of viscoelastic bars, meaning like we will take bars and apply loads to it and see how is the viscoelastic response to them. For this we will use the Alfred's correspondence principles that we discussed in the previous video. So, here is the outline of this video. So, first we will quickly review the Alfred's correspondence principle and then apply it to first analysis of bars under axial load and then move to circular bars which are applied under torsion. So, this will serve as an examples where we apply this correspondence principle and solve some structural problems. So, let us review the Alfred's correspondence principle. We said here we give you 4 steps. If we follow these steps, we can solve a viscoelastic problem. So, the first step is solve the problem using elasticity. So, once we get the solution for this problem in the using the elastic solutions, then we will replace all variables by the Laplace transform. So, here we have shown only strain, but there are other variables in a problem like the stress, the applied load P, the deflection delta. These are the variables in a problem. Next, in step 3 we replace all elastic constants. So, here we showed you elastic constants like the modulus E, which is replaced by S times the modulus in the Laplace domain. But the same can be applied for other elastic constants such as the Poisson's ratio, shear modulus, bulk modulus, to name a few. So, once we replace the variables as well as the elastic constants with this Laplace transform correspondent. So, once we replace the variables and the elastic constant with the Laplace transform values, that is when we move to the last step where we apply the inverse Laplace transform. So, once we apply the inverse Laplace transform, we go from the Laplace domain to the time domain, and the solution we have is the problem solution we are looking for the viscoelastic problem. So, if we follow these 4 steps, we should be able to solve most of the viscoelastic problems, at least those where we have solutions using elasticity. So, let us start with looking what is the, for a viscoelastic bar, if we apply an axial load, how can we find the solutions? So, here is the bar, we are applying a uniaxial load. Let us say this bar is made of cross section A and the material's modulus is E. We apply a load which is P, and let us assume that this is a time varying load. So, we will write it as P of T. So, when we apply a uniaxial load to a bar, we in the elastic using elasticity we know how to write the relations. So, first let us start with step 1, which is the elastic solution. So, how do we find the stresses in the bar? Stresses in the bar is simply applied load per unit cross section. Applied load is P of T by cross section A. Though we know that the cross section decreases, but usually we apply this viscoelasticity, especially the linear viscoelasticity, for very small strains where the changes in the cross section usually can be neglected. So, we will assume at least the cross section area A is constant. And when we apply the Hooke's law, I should be able to write the stress in terms of E times the strain. At least in the elastic solution, E is a fixed value. So, it is not a function of time. The only two which are function of time are the stress and the strain. Even these are changing with time, all because our applied load is changing with time. Okay. And then finally, what is the formula we have for the deflection of this axial bar? It is given by PL by AE. Okay. So, usually you will see in other problems as well, we do not like to have most variables in the denominator. So, instead we want to have these variables in the numerator. So, for that reason, instead of having E in the denominator, I can move it in the above by replacing E with compliance. So, P of T L by A times D, where D is the compliance or 1 by E. Okay. So, these are, let us say 3 equations we will focus on for the bar under uniaxial load. So, now let us go to steps 2 and 3. Okay. So, according to step 2 and 3, we replace the variables and the elastic constant. So, let us focus on the first equation. So, sigma we will replace it with the transform sigma s. Sigma is a variable, P the applied load is also a variable. So, we will replace it with P of s by A is a constant. So, there is no transform to it. Similarly, for the second equation, it will be sigma of s equals, now we have an elastic constant E. So, we said for this elastic constant we will write it as S times E of s, and epsilon is a variable. So, we will simply write it as epsilon of s. Okay. And now, let us come to the third equation, delta of s. P is a variable, we will replace with P of s, L is a constant, A is a constant, and D will represent, since it is an elastic constant, we will replace it with S times D of S. Okay. So, what we have shown here is simply we applied these steps 2 and 3 of the correspondence principle, where we replace the variables and the elastic constants. And now, we can go and apply the last step, which is step 4, the inverse Laplace transform, to find the solution to these 3 equations. But before we do that, let us write it in a more simplified fashion for the last equation. Okay. So, now moving to step 4. Okay. Now, let us see what is the inverse Laplace transform to sigma of s. It is simply sigma of t, 1 by a is a constant, and then what is the inverse Laplace transform to P of s? Again P of t. Okay. So, what did we get? So, once we started from this sigma of t is equal to P of t by a, after all these we ended up with the same equation. So, what does this tell us? This tells that in an equation, if you do not have any of the elastic constants, like in this first equation we only have all of these are variables, sigma and p are variables and a is a constant, we do not have any elastic constant here. So, if there are no elastic constants, we will end up with the same formula. But now, once we move to the second, that is when we see the solution will be very different. So, now let us apply the inverse Laplace transform. So, it should be sigma of t, but now we have this s times product of two functions. Now, again we can apply this convolution integral to write this as integral 0 of t e of t minus u d by du of strain written in terms of u and du. Okay. So, this is simply the definitions we have studied about the convolution integral. So, using that we are able to write this inverse Laplace transform. And now if you notice the elastic solution which is shown here and the viscoelastic solution which is shown here, they are very different. The reason is because we are following this procedure, and because of the viscoelasticity we do not expect to see the same solution, especially when there is an elastic constant in the equation. Now let us apply the same to the last equation for the deflection. Delta of t is L by A. Again we see it is written in terms of S times P times D in the Laplace domain. So, we can invoke this convolution integral to write it as 0 of t d of t minus u and derivative of the load times d. So, essentially now we are able to show you the solution for the stresses in the viscoelastic problem, and we also show the viscoelastic solution to the deformation in the axially loaded bar. But mind you, though we have a solution in the time domain, this is in the time domain, we also have a solution in the Laplace domain. Why I am trying to emphasize this is, depending on the kind of problems you are solving, sometimes it is not always true that you plug in or try solving in the time domain. Sometimes solving things in the Laplace domain will be easier. What I mean is, at the end we need to first substitute here what is the applied load P and the creep compliance D. Depending on the expression, sometimes it is easy to solve in the Laplace domain and sometimes it is easy to solve in the time domain. With few examples we will see how we will use this equation, and we will also see instances when solving in the Laplace domain is easier than solving in the time domain. So, here again we have the same bar, but now the applied load is P naught times h of t, which means it is a constant load suddenly applied at time t equal to 0 and then it remains constant, which is represented using this step function h of t. Now let us try to find a solution to this problem. So, from previous slide we said if you are looking at the deformation of this bar, there are two expressions which we can use, one in the Laplace domain and the other in the time domain. Okay. So, let us try to solve first in the Laplace domain and then we will move on into the time domain. So, here once we notice that P of t is given as a step function, we can apply the Laplace transform and find out what is P of s. P of s is P naught by s. Laplace of the step function is simply 1 by s, that is what we have used to find out the Laplace of the input P of t. Now let us substitute that in this equation. L by A S times P naught by S and d of S. So these both S get cancelled out, and what we is left out is L P naught by A times d of S. Now I can apply the inverse Laplace transform to find the deflection in the time domain. This is simply delta of t is given as L P naught by A times d of t. Okay. So the deflection delta is given in terms of the creep compliance d. Now let us see how we can use this integral to solve the same problem. L by A, now I will still keep this d of t minus u, but substitute p of u. So for this problem we have seen p of u is p naught times h of u, and if we do the first derivative, d by du of p is given as p naught times the derivative of the step function we know is the Dirac delta function delta of so there will be a small confusion. This what we have is the Dirac delta function, and what we are finding here is the axial deformation. Yeah, I know we are using the same variable, we should have avoided that, but now that we have it here, let us try to distinguish. We have this deformation on the left hand side of the equation and the Dirac delta on the right hand side of the equation. Okay. So d of t minus u times p naught is a constant, so I can take it out of the integral, times the Dirac delta function u. Now we can apply the shifting property of the Dirac delta function. What it says is, if you have a function f of t minus u times delta of u, it is simply the function value evaluated at time t. So this can be written as L by A p naught times d of t. So this is the expression we got using the integral form, and this is the expression we got by starting from this Laplace domain. So we see, of course, the solution should come out to be the same because we are solving the same problem. It is just that where we applied this, the given load and the creep compliance. In this particular example, we only applied the applied load. Because of the simplicity of the problem, we haven't even mentioned what is this d of t or what is creep compliance. We haven't mentioned whether it is a Maxwell model or a Kelvin model or some other model. But in the next problem we will see, we will be able to solve the problem only once we mention what is the expression for this creep compliance. So here is another example where we say the load P of t is given as P naught times t, and here we are considering the Maxwell model. So we again start with trying to find the deformation delta. We have one formula in the transform domain and the second formula in the time domain. In this example, we will follow the second formula because we will see that is more convenient for us to solve the problem. but let us see why it is difficult to start from the Laplace domain. So, now if P of t is P naught of t, what is the Laplace of this? So, Laplace of it will be P naught by S square. So, in other words, what I am trying to say is Laplace of t is 1 by S square. So, we use that formula, and here I should be able to write this as L by A S of P naught by S square d of S. So, we can cancel out this with one of the powers. So, we end up with L P naught by A times d of S by S. So, we notice that we have an S in the denominator, and then there is another transform function d of S. So, solving this, doing an inverse Laplace of this is not trivial or straightforward. It becomes the problem, trying to solve this problem becomes more tedious. So, now let us focus on the deformation formula. We have it in the time domain in terms of this integral. So, let us try to substitute this load first. Now that we know P of u is P naught times u, the first derivative d by du of Pu will simply be P naught. So, let us since P naught is a constant, we can move it out of the integral and then write it as du. Okay. To solve further, we need to know what is d or the creep compliance. To proceed further, we need to know what is the creep compliance d. Since we know this bar follows the Maxwell model, we should be able to find out what is the creep compliance for a Maxwell model. From our earlier discussions, this is the formula we arrived at. It is simply T by mu plus 1 by E. Now, let us substitute this in this. So, how will we do? D of T minus U will be T minus U by mu plus 1 by E. So, let us continue here. So, this equation will be L P naught by A integral. Now, I will replace this d of t minus u with this expression here, t minus u by mu plus 1 by E times d evaluated from 0 to t. So, this is now simple integral formulas. So, after evaluation, we should be getting it as. So, once we evaluate this, we should be able to write this as okay. So, finally, the deformation delta of t is L P naught by A times t square by 2 mu plus t by E. So, we are able to get this solution by plugging in or considering the Maxwell model, which helped us to write what is the relation for the creep compliance. Once we plugged it in, we should be able to find this viscoelastic solution for the deformation delta of T. So, now we have been discussing about a bar under uniaxial load. Now, let us look at a different kind of loading, which is considering a viscoelastic bar, we are considering torsion loads. So, let us consider a bar which is fixed at one end, and on the other end we apply a torque T. So, if we look at the end of the bar, this is the initial position and this is after applying torque. And let us assume that this torque is changing with time t. So, and then we said because of this applied torque, there is a rotation at the end of this bar, which is given by which is given by theta. This theta is again a function of time because the applied torque is also a function of time. So, to solve this viscoelastic problem, we will again use the correspondence principle, where the step 1 is to write the elastic solutions. So, we know for torsion bars from the elastics, we simply write it as T by J T by J is shear stress tau by R. R is the radius at which from the mid axis point from where we are looking at the stresses. G theta by L. So, let us define few of these constants. J is the polar moment of inertia, G is the shear modulus. In a while we will come to this third quantity. So, let us write the elastic solution for two quantities, one to find the shear stress and other to find the angle, rotation. First, starting with the shear stress tau of T, from this equation we should be able to write it as Tr by J, but torsion T is again a function of time, R is we are looking at a point R which is fixed by J. And the second equation we will look at is the rotation angle theta, which again from this bottom formula should be able to write it as TL by JG. Okay. So, you may recall earlier I was saying it is better to avoid any elastic constants in the denominator. So, how do we avoid that? We replace it with another term. So, here that term we are calling it as d of g, where d of g is defined as the shear creep compliance. So, like earlier we had this 1 by E defined as d or the compliance. Here we are saying that 1 by g we will write it as d of g. So, it is a compliance for the shear stresses or the shear modulus here. Okay. So, now let us go to the step 2 of the correspondence principle, 2 and 3 in fact, because we want to replace both the variables and the elastic constants. So, starting with the first equation, we replace it with transforms. Tau of S is T of S times R by J, and for theta of S it is T of S L by J is the polar moment of inertia, which is again a constant, but D, which is a material or elastic property, is now a function of time. So, we replace it with d star of s. So, we can replace this d star again as T of s L by j times s times d of s. Okay. Now, let us go to the last step, which is step 4, where we do the inverse Laplace transform. So, here the shear stress is given as T r by j, which is exactly same as the solution for the elastic problem. The reason again is because it does not have an elastic constant. But now if we look for inverse Laplace transform for the angle theta, now we notice that it is in the form of s times product of two functions in the Laplace domain. Now we can use the convolution integral to write it as L by j times g of t minus u times d by du of the applied torque d tu times du. So, this formula should help us find what is the rotation angle theta for the viscoelastic problem. Now, let us do a very small example to quickly apply these equations and see how they are used. So, we are looking at, let us say if torque T is T naught times h of t. How do we find the angle theta? So, let us substitute that. We know that d by du of this applied torque is T naught times the Dirac delta function u. So, when I substitute this into this integral equation, it should give theta as L by j d of t minus u times the Dirac delta function delta of u times du. Okay. And again once we have this Dirac delta function times another function, we can use the shifting property of this Dirac delta function, which by which we get this delta of t is L by j times d of t. So, in our example, we have chosen a very simple load, which is a step function for the torque, and therefore, the angle theta is given as L by j times this compliance, which we defined as shear creep compliance denoted as d of g. So, in this slide we have shown how we can solve problems, how we can solve viscoelastic problems where we have a circular bar under torsion. So, now let us summarize this video. We started by discussing the Alfray correspondence principle, which states that in 4 steps we can start from the elastic solution and end with the viscoelastic solution. So, we have applied that for a bar under axial loads as well as a circular bar under torsion, and showed how we can use these correspondence principles to solve basic structural problems like these bars. In the next video, we will look at how to apply the correspondence principles to solve the beam problems.